Alright, hey guys, what's going on? So this is going to be my first playlist in quantum mechanics on this channel. And what I intend to do here is to basically follow a book as I go through this playlist. And it's this book, Modern Quantum Mechanics. This is the second edition by Sakurai and Napolitano. This is a very good overall book to use. It's a good reference. It's a good, in my opinion at least, it's a good it's a good book to reference, and it's a good book to really get into if you're someone who really wants to get into the nitty-gritty on quantum mechanics. However, with that said, it's not a very thick book. And the reason it's not a very thick book is because many of the mathematical proofs are kind of overlooked a little bit. They tell you, oh, it's trivial that this is the case, and they just keep on going with the material. When we all know that quantum mechanics is not a trivial subject. And so in order to get the most you can out of this book, and even any other book for that matter, I'm going to sprinkle in some ideas from other books, but this is going to be my sort of reference go-to book throughout this playlist. And without further ado, let's get right into this. And so I'm going to be focusing on sections 1.2, 1.3, and 1.4 primarily in this video. And I'm going to maybe go over the big overview of quantum mechanics and why I think the name quantum mechanics isn't necessarily a good one. And I'm going to start on that note, actually. So quantum mechanics, I think, should be renamed to operator mechanics. And the reason why is because when we're told by people like Brian Greene or Neil deGrasse Tyson that quantum mechanics is the physics of the really small, while that is true, it doesn't really help us understand the mathematics. If we actually are interested in going about studying this subject, quantum mechanics really only tells a quarter of the picture, because what we're really looking at is operators. When we get down to the world of the really small, we want to think of operators acting on states. So a particle might be in a state, and an operator, which is, you might think of as sort of this mathematical entity or this mathematical abstraction, this operator acts on the state to produce another state. And what do I mean by that? I mean that if we have some operator here, this is O, I'll just call it O, and it's acting on some state described by a vector like this, it might say rotate that vector. Okay, and so this is sort of the way to think about this, I think, because so the state, again, is described by a vector, and we'll go into why states can be described as vectors. However, I'm going to get a little bit more into this now. If we say that this state can also be described by some name, we'll call it psi, like that. And this operator is acting on psi, and it gives us a new psi. Psi, again, if you're not totally aware with quantum mechanics quite yet, psi is this is a symbol to represent the state that a particle may be in, an energy state, a momentum state, or something like that. This is just sort of the generic way of writing this down. So we have an operator that acts on some state or acts on some vector, and it produces another state or another vector. And you might think, okay, why are we describing states as vectors? So that's the next topic I want to get into. So what I'm saying here is that there's an equivalence between vectors and states, And this is something that isn't really gone over in depth if you go into any textbook or something like that. They don't really, they give you all the notation, they give you all the Dirac notation, all this kind of stuff as preliminaries, but they don't really tell you sort of why this notation works. And so that's what I want to do in this first video. It might be a long video, but if you bear with me on this video, then I think you'll get a lot out of it. I've thought about this a lot. I thought about why Dirac notation works a lot, and understanding this, I think, is going to help us immensely if you're trying to understand quantum mechanics and trying to pursue maybe a career in quantum mechanics. So we have this operator is acting on some state to produce another state. Okay, and so I want to take a look at this state. I want to take a look at this state, and let's say this state psi can be represented as a function. We'll say a two-dimensional function in Cartesian space. If you don't know what that means, it basically means your standard two-dimensional graph, and it looks like, say psi looks like that. It's some function that looks like that. And let's pick some points here. Let's pick this point, and this point. And so this point here corresponds to this point right here on the y-axis. This point here corresponds to this point on the y-axis, and this point here corresponds to this point on the y-axis. Okay, so we have y1, y2, and y3. Okay, so this is point 1, point 2, and point 3. Okay, now let's see how we can represent this as a vector. Okay, so I have I had 3 points here, and so psi now, when we have 3 lines here, we could say this 3 lines means equivalent to but not equals, and I'm sort of using this in not a very kosher way. It doesn't equal a graph or something like that. I'm just trying to show you visually what this thing might look like. So we picked 3 points, so let's put 3 dimensions here. Like this. And right here we'll have y1, and right here we'll have, say y2 is closer to the axis, y2, and say y3 is right here. y3 is right there. Okay? And so what we want to do now is we're going to construct this sort of shape to match up all the points with one another. This is blanking on the name of the shape. It's just like a box shape right here. Okay, and this point that's furthest away from the origin is the point that defines our function. Okay, so we have this point right there. Okay, so psi, which is in red, is represented by a function, but it can also be represented by a vector. Now you might be thinking, well, we only chose 3 points on this function here. If we chose a 4th point, then this function, when we convert it to this space here, is we're going to have to add another dimension, right? And when we add another dimension, that becomes a little bit harder to visualize, but nevertheless we can do it mathematically, right? If we add another point, then we're going to have to add another dimension, and then another point, another dimension, another point, another dimension. And so we could theoretically add all the points up to all together. There's an infinite number of points on a continuous graph like this, and we can construct a vector out of them. It would be a multi-dimensional vector. It would be like a very multi-dimensional vector, but nevertheless it would be a vector. And so we can represent a function as a vector. And so that's something that is very overlooked in quantum mechanics. They often tell you, okay, here's psi. It's a function that describes a state of some particle. Okay. But we can represent that state also as a vector. And when we represent it as vectors, it's easier to visualize how operators can act on vectors. Because if you've taken linear algebra, you understand that a function is basically this thing that takes an input. You can input a vector into a function, and then you get another output out of that. And in this case, we're inputting a vector and we're getting a new vector out of it. Visually, we can think of maybe an operator as rotating a vector in space, okay, or translating a vector in space, or something like that, okay, or rotating and translating. These operators can be very complex, and they correspond to different types of transformations. And we'll realize later that we can categorize these different types of transformations so that we can begin to introduce things like group theory and topology and stuff like that. We can really have a sophisticated understanding of not only quantum mechanics but quantum field theory, quantum topology, and quantum chromodynamics, quantum electrodynamics, and we'll go into that into different playlists. But again, this video here is designed to sort of wet your feet a little bit, to get you to understand some of the abstract concepts that are sort of overlooked in stuff like this book. Again, this book doesn't really go over this kind of detail. So this video is sort of, again, the first video to wet your feet a little bit, to get you introduced to the more advanced topics, so that you can go into quantum mechanics, your quantum mechanics class, with a little bit more confidence. And okay, so I have this vector here. It's all fine and good now. We have a vector here. It represents a function. Okay, so the next thing I want to do is actually one thing I want to add. One thing I want to add is we can think of this as a density also. Okay, and it's this shape that I built. If you think about translating the vector, we can translate the vector, we could transform the vector with an operator. But when we're transforming that vector, think about what's happening. If we're transforming that vector, we're also moving this furthest point away from the origin, and this shape, this overall rectangular shape, or this box shape, could squeeze, it could lengthen, it could heighten, right? And so we're also changing densities. And that's another very important concept to understand when you get into stuff like quantum field theory and even advanced quantum mechanics. Okay, so we're translating vectors with operators, and we're also translating densities as well. Okay, now I want to justify a little bit why thinking about this in terms of operators is a good way of thinking about this. So okay, so we have this. This operator here. It acts on some state, and it produces another state. Now, if I have an operator, and say I have a vector here. I want to do that I actually want to do that in black. So say I have an operator here. Or not an operator, a vector. Okay, I have some vector here, and it's represented by psi. Okay, and now say I have a blue vector here, which is the translated vector. Okay, and I'll call that phi, like that. If you don't know these names here, that's okay. A lot of these are going to be Greek names, Greek and Latin indices as well. We'll get into that later as well. Okay, so we have an initial state right here, and it gets translated to this state, and that translation is done by an operator. And so again, we can represent that as an operator acting on this state here to produce this state here. Okay. And so this is your typical, this is like a standard, okay, this is easy to visualize kind of stuff, but we can also do a translation that looks like this. Say psi looks like this, and say phi looks like this. So this is case 1. Standard, this is a rotation. You could think of this as a rotation. And we'll call this case 2. This is a stretching almost. It stretches, and it stays along the axis of the original vector or the original function. Okay, I'll use vector and function interchangeably, and I'm also going to repeat myself quite a bit because my time isn't limited here. This isn't a class that you actually go into and listen to. This isn't a class. My time isn't limited, so I'm going to take as many videos as I possibly want to and have them be as long as necessary so that I can really hit home a subject or a topic so that you can really understand this material. Okay, so we have a rotation. This is like a stretching. This is like a stretching. And we say that O operates on psi. And I'm using Dirac notation here, okay, where we have this sort of this line and this bracket. This is called Dirac notation. We'll actually get into that as well. We'll go into some more details about that, but I really want to go over the basics right now, and then we'll get into Dirac notation either in this video or in the next video. But I want to do Dirac notation soon because understanding Dirac notation is very, very important in understanding quantum mechanics and being able to compute difficult computations in quantum mechanics. And that corresponds to psi again, because here, this phi here is basically just psi, but multiplied by some number. Right? When you multiply a vector by some number, you lengthen it by that number. So we'll say psi here. We'll say psi is equal to some number a times phi. So I think I'm naming these wrong when I speak about them. A times psi, like that. Naming doesn't really matter that much, though. This is all quantum mechanics. It's not English. Okay, so now this is important. This is an important relationship. So this is an operator. This is an operator. This is an operator. This here, these here are. This here is the eigenvalue. This here's the eigenvalue of our function, or of our operator actually. So wherever we have an operator, we have an associated eigenvalue by which we are translating eigenstates. This is an eigenstate. An eigenstate of this operator. And this is why I want to stress so much operator mechanics, not quantum mechanics. The reason I want to stress that so much is because for every operator, we have an associated set of eigenvalues and an associated set of eigenstates. Okay? There's only a specific set of states that a specific operator can act upon such that they're just stretched. So we're putting a lot of constraints on this, right? So we have a particular transformation or a particular operator that merely just tells you, or it doesn't merely tell you, it tells you everything you can possibly know about what the types of states that it can act upon and the factor by which it can act upon those states. Okay? So everything is dictated by what operator you use. Literally everything is dictated by that. And so I can't stress enough that this is operator mechanics. This is not, while it is quantum mechanics, while we are dealing with the world of the really small, we are also dealing with operators. Okay? And I'm just going to hit that home as hard as I possibly can, because it took me a while as well to sort of come to this aha moment when I was studying this kind of stuff, and I thought, well, this is it became hard to sort of bookkeep everything, to understand exactly what was going on. I felt like I was just memorizing equations and trying to haphazardly understand some of the concepts in here, until I came to this aha moment, and I was like, oh my god, this is quantum. That this isn't quantum mechanics, this is operator mechanics. If I just keep track of the operators, okay, then you could theoretically come up with any state. You could theoretically come up with any state that operator can act upon such that the state is just stretched. Right? And that's really what I really want to head home here. This idea that operators are what we're dealing with. Operators. This is operator mechanics. Okay, and so then now we have this notion of an eigenstate and an eigenvalue. Eigen in German means true. So for every operator, there's a true value associated to it, and also associated to its corresponding eigenstate. Okay? Now, I'm going to give examples of operators. You might be thinking, okay, this is all fine and good. This is really general. I haven't really come across quantum mechanics yet. But, okay, what are some examples? Examples, again, are important. So examples of operators are the position operator, for example. Position operator, and I'll go into why the position operator is like this, but the position operator is basically a derivative. Okay, position operator is basically a derivative, ddx. This is an example of an operator. Okay, and again, I want to abstract things a little bit too, because this is going to be sort of the next deep topic, subtopic within this lecture. So here we have, I'm just going to title examples of operators. Examples of operators. ddx, so the derivative of a function. So this is number one. ddx is a derivative operator. When we take the derivative of a function, we get another function out of that. Okay, so we've basically operated on a function, and we got another function out of that. Okay, and this is the derivative with respect to space. Another one is the derivative with respect to time. Derivative with respect to time. Okay, we can do that as well. we get a function in terms of time, and we can operate on that function, and we get another function. So we've operated on a function to give us another function. Okay, so this is another example of an operator. And in quantum mechanics, we're putting some i's in front of these operators and some h bars and all that stuff. But I'll go into that later. Another example of an operator would be the Laplacian. If you don't remember what the Laplacian is, it's basically the second derivative with respect to space. So we could take a second derivative of a function, and we get a whole other function. All right, and that function that we get in particular is associated with curvature. Okay, and we'll get into why curvature is important. But again, the point is that these are all examples of operators, and they help us translate between functions and between different functions. Okay. Another example, well, you might be thinking, how about the integral? If you've taken calculus, and I'm assuming that you have taken calculus. If you're in this watching quantum mechanics, I'm going to assume that you've taken some calculus. The integral dx. Again, this mathematical object, acts on a state, or it can act on a function, and it will give us another function, right? And again, whenever I say function, I also mean vector, because we can represent a function in terms of a vector, just like we did up here. Okay. And I might add, actually, that this is Cartesian space for some vocabulary and some history. Cartesian space, I think this was developed by René Descartes. Don't quote me on that, though. Cartesian space, and this is Hilbert space. So we have a Hilbert space associated with a function in Cartesian space. Okay. So whenever I say function, I also mean to say vector. So we're translating functions much like we're translating vectors. It's just easier to understand functions as vectors because it's easier for us to understand, okay, the rotation of a vector as opposed to the rotation of a function, right? But nevertheless, it's pretty much the same thing. We're just abstracting our mind a little bit and thinking about that. Another very important example of an operator is an inverse. So number 5 here, we have an inverse. So say we have some function and its inverse. Now this one's particularly important, especially when we begin to get into general relativity. Okay, we have this notion of a function, and when it's applied to its inverse, we get most often the number 1. And this is really, really important because we go from a vector to a scalar. Okay? And in this particular case, we're going to this scalar 1. And so the reason that's important is because that's a special type of transformation. It's a special type of transformation. It takes us from it reduces dimensions, basically. We've reduced our dimensionality of a vector in some sort of Hilbert space to a single number. Okay, and a number exists only in one dimension because it only has one component to it. And it shows up in general relativity as something called a covector. So a vector applied to its covector will produce a number, and in particular we're looking at a real number too. So there's a lot of constraints on this. We have that this number 1 is real, it's not imaginary, so there's no i's in here. Okay, and it's generated by an operator when applied to a function. Okay, and then you might think, well, which one of these is the operator? Is it f of x or is it f inverse of x? And And the answer is yes. Both of these are sort of operators. One, you can think of f of x as operating on f inverse of x, or you can think of f inverse of x as operating on f of x. Okay, one of these is the state, and the other one is the vector that's being applied to that state. Okay, and so this is a good segue into the next topic I want to talk about, which is the idea of not a covector, the idea of Dirac notation. So let's get into Dirac notation now. So I've denoted a vector to look like this, okay? And this is called a ket vector. A ket vector. And so you might think, okay, let's say this inverse might be the ket, okay? So this inverse might be the ket. So how would we represent the non-inverse? This one right here, this guy down here. Well, we would represent it like this. Same vector, just like that. And this is, don't laugh, the bra vector. Paul Dirac, who was famous during the 1920s, came up with this notation. And it's called bracket notation. He wasn't very clever in naming this type of notation. But when these two things are applied to one another, we can get something like this. All right. So we have this is the bra vector and this is the ket vector. Together they make a bracket, and that's how this is denoted. And if you remember anything from vector calculus, we remember that if we have two of the same vector and we're dot product, this can be thought of as a dot product. If we're dot producting a vector with itself, we get 1. Okay. So these two things are this is the statement saying that these two states are the same exact state. Okay. Likewise, if we have two orthogonal vectors, two vectors that are not mutually inclusive with one another, they're orthogonal or 90 degrees from each other. In other words, they don't have they're not sharing components with one another. We say that as, say, this vector is completely orthogonal to maybe this vector. Right, one is 90 degrees from the other, and we say that that is 0. So these are two very important topics, or very important sort of equations. Not really equations, they're relationships. Okay, and if we're going to abstract this a little bit, we can think that we have some state phi or psi bracketed with itself, and that, again, if it's with itself, it's 1. Likewise, if we have a different state that's orthogonal, orthogonal means 90 degrees or perpendicular, shares no components with. Shares no components with phi here, then that is equal to 0. So this is sort of a notion of kind of parallelism, and this is a notion of orthogonalism, if you want to think about it like that. Okay. And so again, so we could think of So we can think of it like that. So we have this inverse, and we have its corresponding, we have its corresponding non-inverse here, and we get a single number out of these, right? So we're translating a vector to another vector, and we're finding out that we get a number out of them. Now, if we get 1, then that means the two vectors are pretty much the same. If we translate one vector from here to here, we're basically multiplying, we're taking the square root of that, or not the square root, we're squaring that vector, okay? And when we square things in probability, we'll find out that quantum mechanics is also probability mechanics. When we're square rooting things, we find out that we want to get 1 out of that. That's a probability concept, something that I'll go into a little bit later, maybe in a probability playlist. And when I'm talking about this case right here, again, we're translating to a scalar, but this scalar happens to be 0. Okay, and when it's 0, that means the two things do not share any components with one another. Okay, and so we can think now, what if we have something that looks like this? Psi final, perhaps, and psi initial. So we have some initial vector that describes some initial state, and we have some vector that describes a final state. And we want to figure out how these two things are similar to one another. Okay, and we could get a number. Say we got like 0.95. Okay. Now I was giving you a little bit of a misnomer here. So we're comparing the initial and the final states when we're doing this bracket notation. If we actually want to see the translation actually happening, and not just comparing the end and the final, then we have to sandwich the operator in between these two states here. Okay, so we can get something like this, which means that psi here, or phi, or whatever you want to call it, the final state is very close. It strongly agrees. It has most of its components are shared with the initial state here. What if we get something very close to 1? If we get something not very close to 1, maybe very close to 0, that means the two states, there's a very dramatic change between the two states. Okay, so again, this is operator mechanics. We're operating on states, we're operating on vectors, and we want to see how, and in this case, we're looking at how the initial and the final compare with one another, how the initial states and the final states compare with one another. And so I'm going to erase a few things. I'm going to erase some of this here to give myself a little bit more space. I want to go over just one more concept here. While I'm erasing, again, think of this as an operator mechanics. Operator mechanics is, I think, going to do you a little bit more justice in understanding exactly what's going on when we're talking about this kind of stuff, when we're talking about quantum mechanics. Because again, if you don't think of this about operator mechanics and translating states between states and stuff like that, then it's going to be really hard to understand scattering, for example, which is a more advanced topic and something that we'll go over later. But it's going to help because, again, when we're scattering, I study cryo-electron microscopy, and that's a good application of scattering, where you go from one state, some particles in some state, it collides with some particle, a protein or something like that, and it gets translated into another state. Okay, so the scattering event, there's a lot of information packed in that scattering event. If we can understand what the final state was and the initial state was, we can understand the complexities behind that operation that occur at the collision with the protein or the chemical or something like that. And so what I want to just go over a little bit now is this idea of, so we talked about kets and brackets and bra vectors and stuff like that. I want to go over now this idea of an operator within the bracket and ket space, if you will. So if we have some state phi and we're operating on that state, say with this generic operator again, actually I'm going to do a tangible example. We're operating with this operator here, and we get we get a final state out of that. So I'll put initial here. We get a final state out of that. We can think of this as, okay, this operator translates this vector or this state or this function such that we get a final state. We don't exactly know what that state is. But the inverse of this state here is the ket. So if we were to sort of divide things a little bit, if you will, if we wanted to take this here to this side, we would get something that looks like this. Something like that. If we were to divide this by itself, we get 1. And so what is this object? This object is, well, okay, let's make sense of this. So we're operating on I, and we're getting phi out of it. So we're going from here to here via this operator. And actually, I said I was going to stick with an actual example. ddx. So we're operating on this with this, and we're getting this out of it. So we're kind of reading from left to right, not from right to left as we usually do in like a book or something like that. But we're reading like that. And you might think, okay, so I has some components here. So this thing will have some components, and this thing will have some components to it as well. Because again, vectors they have components to them. And so what this is basically is this can be summarized as a matrix. If this thing has components and this thing has components, we can summarize this in terms of a matrix where we have something that might look like this. And I'll just give us a cut. I'll just write the first few examples here. So we have psi 1 d dx psi 1. So this is the translation of the first component into the first component of the final state. Okay, and if we go along the diagonals here, our next entry in this matrix would be 2 d dx like that. And we can continue going down. I'll go down another example here. So this would be 2 and 1. So this here, this I corresponds to the row we're going down, and the final corresponds to the final corresponds to the column, or my bad. So the final corresponds to which row we want to read down, and the initial corresponds to which row, or to which row we want to read across. My language is a little bit off today. And this can go for as many components as there are in the final state, and this can go for as many components as there are in the initial state, and we get this matrix like this that looks like this. Okay, and so now what I'm going to do is I'm going to erase a few things down here. This is my first video, and so I'm sort of trying to develop a way by which I can keep some stuff on the screen, or most of the stuff on the screen, while doing this in a way that I think is most effective. And right now, erasing everything like this, I don't think is necessarily a very time efficient way of doing things, but bear with me here. This is my first video. I'm trying to figure things out. Okay, so I want to contrast this. Actually, I'll erase this too. I want to contrast this matrix with another example. Oftentimes, we'll write this matrix as equaling something that perhaps looks like this. If our operator again is d dx, it has components to it now. So this thing has components to it. It has final components and initial components to it. And so this thing is a matrix. This thing is a matrix. Okay. So operators are matrices for the time being. And the reason I say for the time being is because we're going to have to abstract our thinking a little bit more. And we're going to really just have to think about them as these mathematical entities that kind of just translate things. But it's good to sort of understand them as matrices, because again, matrices are they're good ways of doing translations. If you've taken linear algebra, then you can understand that a matrix is something that can rotate a vector, or it can translate a vector, or it can stretch a vector, depending on what the components are. It can render a vector the same. There can be no translation, and that's another interesting concept. There can be, so a translation can be the lack of a translation. It just stays the same. Translation can be rotation, vibrations, or anything, or something like that. We can think of any possible transformation that any possible vector can go through. But again, these are matrices. So as a summary now, I'm pushing an hour here, and I don't think I want to exceed an hour. I want to now go through just summary. So operators can be thought of as functions, so vectors. Okay, so we went over how a vector can, when applied to itself, yield a function or a scalar, right? So that's another type of translation. So a vector applied to a vector. So one of those vectors is the operator, or the mapping. You can also call it a mapping that maps a vector into a scalar. Function does the same thing. A function will take an input and it yields an output, right? States are kind of the same way. States can be thought of as functions, but really I'm getting I want to I really want to hit home this idea of operators. But states can be thought of as functions and vectors as in the same way. And they can be thought of as matrices. Okay. And so I don't want to exceed an hour here because I think once, in my experience at least, many of you who see that the video is over an hour tend to not want to watch it because it takes too much time. With that being said, I think this is a good primer on how we can begin to think about quantum mechanics. Again, I went over this book a little bit. I started off with chapter 1, but I'm breaking things down into a lot more detail so that reading something like this will be a lot easier. Okay, so I kind of touched on some topics in chapter 1, but I'm going to go over some more chapter 1 stuff in later playlists. And again, this is just going to be something I'm going to be referencing. I'm not going to parallel it. I might deviate. I might bring up some papers that are interesting and have those be lectures within themselves as well, just to really help you understand this kind of stuff later. And without further ado, I hope you've enjoyed this first topic in quantum mechanics. Thanks for watching.